with 6 talks dedicated to vortices. I should remind people that so today the lunchtime is just 1 hour. So at 1 o'clock, Ignasi is going to give a colloquium here. So it's a broader talk, broader audience talk, reviewing the vortex invariance. But yeah, so Ignasi now is going to talk about nonlinear vortices on nearly nodal curves.
Okay, so thank you very much for the invitation to give a talk here. I will begin by reviewing the nonlinear vortex equations. Assume that X is a compact symplectic manifold and that there is a Hamiltonian action of the circle on X. I denote by mu the moment map. I will identify the target of the moment map, which is in principle the dual of the Lie algebra of the circle with the Lie algebra itself. Suppose that sigma is a compact Riemann surface and nu is a volume form on sigma. And finally, let's take an S1 invariant almost complex structure on X, which is compatible with the symplectic form. Such structures always exist, and they are unique up to deformation. The space of these structures is in fact contractible. Now the equations are the following. Suppose that P is an S1 principal bundle over sigma. A is a connection on P, and phi is a section of the bundle associated to P with fiber X. Now consider these two equations. On the one hand, you require that phi is holomorphic with respect to the connection A, and of course here we are using implicitly this almost complex structure. And then we also require that the curvature of the connection plus the volume form times the moment map evaluated at phi is equal to 0. Okay? I will call these equations vortex equations. This is maybe not a completely standard terminology because usually the vortex equation is only the second one, but just to save time, I will say that these are the vortex equations. Or you can call it the nonlinear vortex equations because the target is X, which is a compact symplectic manifold, instead of a vector space, which is maybe a more usual choice. Of course, the meaning of this expression here is the following. So the moment map, by its very definition, is S1 invariant, and hence allows to define a map from the associated bundle with fiber X to IR, and then the meaning of this expression here is simply the composition of phi with mu. Okay. So these are the vortex equations, and the problem I want to consider involves two important theorems on vortex equations, mainly on compact Riemann surfaces. On the one hand, a compactness theorem which considers also the possibility that the Riemann surface changes its moduli and becomes eventually nodal, and on the other hand, the Hitchin-Kobayashi correspondence. So let me first talk about the compactness theorem. So I will state the theorem in a very particular case, but which is enough for our purposes. Suppose that X is a family of prestable curves and by this we mean the following. So X is a smooth complex surface. The only critical value of pi is 0. Well, let me say first that pi is proper. So pi proper means that all the preimages are compact, sorry. And its only critical value is 0. So D denotes the unit disk centered at 0. And we also require that near a singular point of pi, the map is modeled on the following simple map. So we assume that near each critical point of pi, there are holomorphic coordinates, say x comma y, with respect to which pi is x times y. Okay. Now then, for each t in D, the preimage of pi is a compact Riemann surface. Ct is smooth for any t different from 0, and C0 has at most nodal singularities. Okay. Now, our aim is to consider the vortex equations on this collection of curves, but to define the vortex equations, we need a volume form. So we need to specify what volume forms we are going to consider on these curves. And our choice is the following. So we assume that nu is a two-form, so a smooth two-form on X, such that the restriction of, so its restriction to each of the curves is a volume form for each t. So this is, the meaning of this is clear when t is different from 0. When t is equal to 0, what we really mean is that nu 0 defines a volume form on the normalization of C0. Okay, so this is the setting, and as I said, this is much more restricted than the general theorem I'm going to mention afterwards. So now consider the following problem. Suppose that Tj is a sequence of elements in D converging to 0. Suppose that Pj is a line bundle over the curve over Tj, which I denote by Cj. Suppose that Aj is a connection on Pj, and phi j is a section of this bundle. And now the assumption is that this triple, Pj, Aj, phi j, satisfy the vortex equations. Well, the question is there any possibility of defining a limit object over C0? Of course, unless we impose some a priori bound on, say, the energy of these objects, in general, there will be no hope of having a limit object. A way to impose an energy bound is to restrict the topology of the objects. Okay, so we assume that Pj is isomorphic as smooth principal circle bundles to a fixed P for any j, and that all phi j's, which can be seen as sections of a fiber bundle which is independent of j, are cohomologous, or homologous, sorry. Which, by this I mean that if I push forward the fundamental class of sigma, so that I get a class here, this is independent of j. Now, this implies that the so-called Yang-Mills-Higgs functional of this triple is uniformly bounded. Okay, so now the theorem I want to, the compactness theorem is the following. So this is joint work with Gang Tian. Roughly speaking, it means the following. Up to passing to a subsequence, the sequence converges in a suitable sense, which I'm not going to make too much precise, to the following kind of object. On the one hand, we have a principal bundle, but this bundle will be defined not necessarily over C0, but over C0 plus a collection of bubble trees attached to it. A connection on P, this connection will not necessarily be smooth. In fact, it will be defined on the smooth locus of C naught tilde, and the property that this connection will have, and this will be a consequence of the fact that this connection arises as a limit of connections like those, is that its curvature extends continuously across the nodes. And also, this will play no role in my talk, but in general, the connection will be flat on bubbles. Now, these will be properties of the limit connection, and then we will get a section phi also. So phi will be as A, it will be defined on the smooth locus of the curve. It will be holomorphic there, and it's going to extend continuously not as a section of the bundle over C naught tilde, but on the normalization. But the important thing is that if you take a node in C0 tilde, it will have two preimages in the normalization, and the continuous extension of phi doesn't necessarily take the same values at the two preimages of the node. This makes a crucial difference with Gromov-Witten theory. So you will have in general, if this is the normalization and this is x, so phi will send possibly one preimage of the node to one point of x, the other point to another point of x, and not even the S1 orbits need to be the same. Now, in fact, there might be extra objects which are naturally defined in the limit, and one of them will be gradient flow lines. So these gradient flow lines will precisely connect to the two preimages of each node. The values of phi at the two preimages of each node. Okay, so these are objects which appear naturally as limits, and then there will be some gluing data, but I'm not going to talk about this. So what's important is that these gradient flow lines connect the images of the extension of phi to preimages of nodes. Okay, so this is roughly speaking the statement of the compactness theorem. An explanation of what is going on is the following. So suppose that we take a curve CT with t very near 0, so that this curve is nearly singular. Now, ignoring the fact that that phi is a section of a bundle, let's think that phi is a map from the curve to x. Okay. Now, what is going to happen is the following. If you look at the neck that it stretches approaching a singularity here, its image in phi, in general, will concentrate along a gradient flow line of the moment map Yeah, I set a gradient flow line, but not of what function. This is a gradient flow line of the moment map. Okay. But the issue is that this gradient flow line can have arbitrary length. Okay, and so this, as I said, this is very different from the situation in the usual Gromov compactness theorem for pseudoholomorphic maps, because in the context of pseudoholomorphic maps, you have a priori bounds on the diameter of the image of a neck like that. Okay, okay, so this is the compactness theorem. Let me, excuse me?
The bubbles that you told us about.
Yeah, well, the bubbles are essentially like in Gromov-Witten theory. Okay, so you can think that, for example, it might happen that if you look at what is the image of small d here, eventually if the energy concentrates here, the image could be something like that. Okay, so but this is exactly like in Gromov-Witten theory. That's why I didn't want to give details here. Okay, so this is the compactness theorem, and what we have to keep in mind, and also, sorry, there's something also important. I mentioned that the limit connection need not be smooth on the nodal points, and the reason is very easy to understand. As you approach as t goes to 0, you can compute the holonomy of the connection around the neck. There is no reason a priori why this holonomy should converge to the identity as the curve becomes nodal. And this is the reason why, in general, you will have, let's say, a meromorphic connection in the limit. Okay, so and then there will be a well-defined limit holonomy of the connection A around each node. Okay, so these are the two issues which we have to keep in mind. That in the limit we have meromorphic connections with a non-trivial holonomy around the nodes, and also these gradient flow lines of the moment map. Okay. Now let's talk about the Hitchin-Kobayashi correspondence.
Points that the preimages of nodal points map to the endpoints of the gradient flow lines. That the critical points.
Endpoints.
Not finite pieces of the gradient lines. They're not
finite or infinite. Yeah, but a priori the extremes need not be fixed points of the action. Yeah.
What do you mean by extending continuously to form across nodes?
Sorry, this?
No, FA.
Across across the normalization. I mean, yeah. So the curvature is a to form on here. You pull it back to the normalization. Sorry. On the smooth locus. Okay, you pull it back to the smooth locus of the normalization, and then I claim that this extends continuously here.
So the normalization is smooth, right?
Yes. Because they are nodal singularities.
But you said smooth locus of the...
Sure. Yes. Well, sorry. By these, what I mean are the preimages of the smooth points in the normalization. Sorry.
Just points that are going to be identified.
Exactly.
The curvature will have the same value.
Yes.
What are you saying?
No, I'm not saying that.
No?
So you have something like that, okay? The curvature is defined away from this node. You pull back everything to the normalization.
Yes.
And the statement is that the curvature extends across here and across here.
On each branch?
On each branch, yes. But I don't say that there is any relation of the extensions.
Yeah.
Okay, so now let me talk about the Hitchin-Kobayashi correspondence. So now let's assume that X is scalar, and this means that the action of S1, X scalar, I mean that X omega I is scalar, so the almost complex structure is indeed scalar. So the circle action extends to a holomorphic action of C star. Okay, and this has the following implication. If you have a principal bundle with a connection A, you can complexify the principal bundle by making a twisted product with C star, and then the del bar operator associated to A defines a holomorphic structure on Q. Okay, so by the way, this is not the first time in the conference that Hitchin-Kobayashi correspondence is mentioned. It appeared also in Oscar's talk. But this is a it's slightly different from the correspondence he was referring to, and it's a very concrete situation. Okay, so P and A give rise to a C star holomorphic principal bundle over sigma, and now phi can be identified with a holomorphic section of this holomorphic bundle. Okay. Consequently, from a triple PA phi, we obtain a pair Q phi which is a holomorphic object over sigma. Now, the Hitchin-Kobayashi correspondence answers the question of whether we can go back here. So if we are given a holomorphic C star principal bundle and a holomorphic section of the associated bundle with fiber X, is it possible to recover a reduction of the structural group of Q from C star to S1 so that if A is taken to be the Chern connection, that is the only connection which is compatible with the holomorphic structure and the reduction of the structural group, then the triple PA phi satisfy the vortex equations. Okay. Now, in order to answer the question, we have to introduce a stability condition, or say polystability condition. So Q phi is polystable if the following holds. We require these two inequalities. Okay. So these inequalities are the analogs in our situation of the Mumford-Takemoto stability, or polystability, rather. Okay. Let me just briefly comment that this is well defined, and this is also well defined, but it's not completely obvious. The thing is that the moment map mu will never be invariant under the action of C star. So mu does not define a map from the total space to IR. Okay? So this is not well defined, but it does define a map from the fiber bundle with fiber the fixed point set. Okay, and it turns out that these limits lie in the fixed point set. So this is really well defined. Okay, now the theorem, and this is the Hitchin-Kobayashi correspondence, says the following. Given q comma phi, there exists a reduction, let's call it H, of the structure group of Q from C star to S1, such that if we set P to be equal to the associated bundle, associated S1 principal bundle, so the set of Q's such that Q S1 say is equal to H of pi of Q. Okay, so pi is a projection from Q to sigma. So setting P to be the S1 principal bundle associated to H, and H the chain connection, the triple PA satisfies the vortex equation. So there exists such a metric H if and only if Q comma phi is polystable. Okay, so this is the statement of the Hitchin-Kobayashi correspondence. It is an existence result. A priori, it doesn't give us any information of what the reduction looks like. It says that the reduction exists provided the pair is polystable. Okay, so now we can state our problem using the notation of the compactness theorem. Suppose again Tj points in the disk, in the unit disk converging to 0. Suppose that Qj phi j is a holomorphic pair of that type on Cj. And we make the same assumptions as in the compactness theorem, namely that all Qj's are isomorphic. Now, as C-infinity bundles, we are not talking to the on the holomorphic structure to a given C star principal bundle, and suppose that all phi j are homologous in the same sense as before. Suppose, furthermore, that that all pairs are polystable. Then one can associate to these pairs reductions of the structure group, defining triples Pj, Aj, phi j, which satisfy the vortex equations. These triples will satisfy the restrictions that I was imposing in order to consider the possibility of defining a limit, namely that all Pj's will be isomorphic as a smooth principal circle bundles, and all phi j will be homologous. Another question is, so by the compactness theorem, up to taking a subsequence, we can assume that these triples converge to a limit object. Okay. Okay, so a bundle P over C0 with maybe bubbles attached, a connection A and phi, and gradient lines. Let me ignore the gluing data for the for this talk. Okay. Now the problem is, can we understand this limit point by only looking at the holomorphic pairs? For example, to be more precise, is it possible to know whether there will appear a gradient flow line? Is it possible to know whether the connection A will really be singular at the nodes by only looking at the holomorphic data? Of course, this problem is not immediately easy to solve because, as I said, the Hitchin-Kobayashi correspondence is an existent result. It doesn't tell us how to find H. In fact, H will be a solution of a PDE, so it's not immediately clear how to compute the solution explicitly. So we should think as a Hitchin-Kobayashi equation as something difficult to solve. And consequently, what we would like to do is to describe the limit without necessarily solving the equations. So this is what I'm going to try to explain in the remaining time. And the basic idea is that although in general we won't be able to solve the Hitchin-Kobayashi equations, we will be able to solve to extract some crucial information of the solution H out of the algebraic data. And this will be enough to describe the limit. So to make precise what I mean by finding some part of the information on H, I will relate the Hitchin-Kobayashi equation to the Laplacian. This is something quite standard and is the underlying idea in the reduction of the Hitchin-Kobayashi correspondence, for example, for abelian vortices on Riemann surfaces to the Kazhdan-Werner equations, which Oscar mentioned. The idea is the following. One takes H naught, so say given Q phi, one considers reduction H naught. You can think in terms of a Hermitian metric on a holomorphic line bundle if you want. Whose curvature, the curvature of the reduction means the curvature of the Chern connection, is the following. So we assume that the curvature is constant with respect to the volume form. Okay, then you can describe all possible reductions as H naught times the exponential of some real valued function, and the statement is that this H solves the equation it's important to take into account that the second term also involves H. Okay, if and only if we have the following equation. Okay, so this is completely parallel to the reduction to Kazhdan-Werner equation. Okay, so this is the equation what we have to solve, and it involves the Laplacian, and then the term on the second on the right-hand side is nonlinear on U, but it involves no derivation. Okay, now an important thing is the following. So this is a constant. And, well, this is not a constant in general, but this is a bounded function. Because we're assuming that X is compact. So the values of the moment map are bounded. This is uniformly bounded. So whatever solution of the Hitchin-Kobayashi we have, we know that this Laplacian is bounded. Of course, what we would like to know is whether we can extract from these bounds on U itself. And in order to be able to do that, we need to control the spectrum of the Laplacian. Okay? So this is the, by this I mean the analyst's Laplacian. Okay? Now we have the following theorem, but we will restrict attention to a, oh my God. To the following particular case. So I will denote by C tau for any tau in the unit disk. Sorry, and what I'm going to explain, well, no, not so far. No. So we consider these curves here. So these are this is a family of conics in CP2 degenerating to a nodal curve when tau goes to 0. And then I consider the restriction of the Fubini study symplectic form on CP2 to CT, normalize so that its integral is equal to 2. Okay. Now I have the following theorem. Let lambda t naught t1, sorry, tau 2, etc., be the spectrum of minus delta counted with multiplicity. Then, of course, the first eigenvalue will be 0, corresponding to the constant. And the non-trivial statement is the following. On the one hand, we can control at first order the first eigenvalue in that this quotient converges to 1. Okay? And second, all the other eigenvalues are uniformly above 0. Okay, so they are bigger than some constant. Independent of tau, and this for any j. Okay? So if you think of the spectrum of the Laplacian as the curve approaches a singular curve, except for the first and second eigenvalue, all the other eigenvalues will stay away from 0, and the first eigenvalue will be all the time 0, and the first eigenvalue behaves like 4 pi over log of tau. Okay, and now, so what does this mean if we think about the Hitchin-Kobayashi correspondence? Well, if we look at this equation, this means the following. It means that, say, if U is the solution to the Hitchin-Kobayashi equation, or say to this equation more properly, and you write U as a linear combination of eigenfunctions of the Laplacian, we will be able to control the piece of U, which is a combination of eigenfunctions of eigenvalues beginning at the second eigenvalue. All those we will control, but we will not control the part of U which is a multiple of constants, and the part of U which is a multiple of the eigenfunction corresponding to the first eigenvalue. Those two pieces of view will be the ones which, in fact, we won't be able to control immediately by looking at the equation, but those will be precisely the responsibles of all the phenomena that can appear in the node. Okay? So let's now consider a particular case. And now what I'm going to explain now is joint work with Guangbo Xu. Suppose that X is CP1. The action is the following. And the moment map is this one. Okay, so here there is a parameter and one of the things we will see is that the limit behavior of the solutions depends crucially on this parameter. There will be a wall-crossing phenomena. Okay. Now I take Qj to have degree 1. Okay. I consider phi j will be a section, a holomorphic section of Qj of this associated bundle, but this associated bundle can be identified with the projectivization of O1 plus O, and hence you can think of phi j as in homogeneous coordinates as given by a section sigma j of this guy. And now I will give a description of all possible degenerations in the limit in this particular situation. Okay, so let Aj denote the preimage of 0 of the vanishing locus of sigma j, which will be a unique point in C tau. Okay, and now I will only be able to state the result we get, but won't be able to give you any argument. So the theorem is the following. Well, sorry, before stating the theorem, let me point out that this is stable, well, say polystable, if and only if this parameter zeta is bigger than pi. Okay? So take zeta bigger than pi, and we immediately know that all pairs are stable. And now let x minus be this point in C tau. Okay? And now the theorem is the following. Suppose that, so the sequence of objects are uniquely determined by the sequence of points Ej. Okay, we are going to consider the possibility that Ej stays away from say at bounded. Let me see. Well, let me also define x plus. Okay, so we consider only two possibilities. Either Ej stays bounded away from x minus and x plus, or it converges to x minus. The other case, which is when it converges to x plus, is completely symmetric to the second case, so I don't explain it. So suppose Ej stays away from x plus. This can be, you can take here the metric in CP2 given by Fubini study metric, okay? And suppose that this is of the order of tau to the gamma, where gamma is non-negative, okay? Suppose we have this speed of convergence, then we distinguish two cases. if pi is bigger, sorry, if zeta is bigger than 2 pi, so not only bigger than pi, but bigger than 2 pi, then in the limit, we get the following. If gamma is 0, so that Ej, say, stays simultaneously away from x plus and x minus, the limit object I describe this way, and by this I mean the following. So the curve C0 is a rational, is the union of two copies of CP1, and I read this note this way to mean that here the connection is meromorphic, and the holonomy of the connection here is -1. Okay. If gamma is between 0 and minus and 1/2, we get something similar, but as gamma moves from 0 to 1/2, the limit holonomy changes continuously, and in fact it is equal to the exponential of 2 pi I multiplying -1/2 minus gamma. Okay, and finally, if gamma is bigger or equal than 1/2, in the limit we get something like this. So we have on one side on one irreducible component of C0, we have a vortex like the ones we consider, so of degree 1. Here the solution is trivial, and in general we will have a gradient flow line connecting both. So this is what happens when, sorry, may I have 2 more minutes to, okay. Okay, so this is what happens when zeta is bigger than 2 pi. These are the possible degenerations according to the speed of convergence. On the other hand, if zeta is smaller than 2 pi, then we have the following. So if gamma is equal to 0, we have something as in the previous case. If gamma moves from 0 to this number here, we get also same idea like as there, same limit holonomies. But the big difference with the other case is that as soon as gamma is bigger than this number, the limit object doesn't change. It will always be the same. So the residue, the holonomy here, is the exponential of 2 pi I multiplying -1/2 minus zeta minus pi over 2 pi. Okay, so when zeta is smaller than 2 pi, you don't reach these objects here, and this is quite natural because with this zeta, with these values of zeta, if the total volume of the CP1 is equal to 1, which is the case of the volume induced in the irreducible components of C0, then the objects are not stable. So there can't be solutions. So the existence of these solutions are, in that case, prevented by the stability condition. And to finish, let me draw a picture of what are the moduli spaces. So the set of isomorphism classes of objects has a natural topology, and it can be described as follows. So when zeta is bigger than 2 pi, in that situation there, the moduli space of limit objects is a union of 3 copies of the sphere. So this thing here parameterizes objects like this. This here parameterizes the symmetric objects, and this here parameterizes the objects with meromorphic connections. Okay. Whereas if zeta is between pi and 2 pi, the moduli space is simply a copy of the sphere, and all it parametrizes are objects like this. So we see a wall-crossing phenomenon in that case. Unfortunately, well, this is what we can obtain by exploiting the description of the eigenvalues of the Laplacian in the limit. Unfortunately, I don't have time to give you an idea of how we deduce this information. Well, thank you.
Before the limit, the moduli space is always a sphere. For C tau non-zero, the smooth.
Yes, of course. Yes. Right, that's a good point. Yeah, if the underlying curve is smooth, then the moduli space of vortices is in degree 1 is just a copy of CP1.
If you replace the circle by a compact Lie group, what changes in your picture?
Well, many changes. In fact,
So it's like a torus of higher dimension, let's say.
Yeah. Well, I've never studied in depth the general case. If you are working with abelian groups, then the theorem for the eigenvalues of the Laplacian will be, I guess, enough to get a description. But I can't give you any statement.
But what is the substitute of gradient line?
Well, that's. I mean, in the abelian case, it will probably be a gradient flow line of the composition of the moment map with some projection to R. Okay. In the case of non-abelian Lie groups, I'm not really sure.
So this moduli space will have also Kähler metrics, and then you can think about the information as you reach the nodes. Have you got anything to say about that?
No. Yeah, I mean you can consider the L2 metric, for example, but I mean when you study the deformation theory of these vortices with meromorphic connections, typically you need to consider weighted Sobolev spaces, and I'm not completely sure that the resulting metric is not sensible to the choice of weight. I don't really know. I never thought about it, but it could be that in the smooth case, when there are no nodes, there is a natural choice for the L2 metric. It could be that when you consider these vortices with singularities, the L2 metric depends on the choice of weight.
Any more questions or comments? So let's thank you.